All right, so we're in lecture set 2 right now. Lecture set 2 is a review of confidence interval construction and hypothesis testing for a single population mean. So the idea here is that we've collected one sample. We're interested in estimating the population mean mu, and we can do this in two ways, via a confidence interval or via a hypothesis test. Now the hypothesis test the hypothesis test isn't actually an estimating procedure in the same way that a confidence interval is. So with a hypothesis test, we're not going to end up with a range in which we think the true numbers are going to fall. What we actually end up with is a answer to a question that we pose about the parameter of interest. So the hypothesis test and the confidence interval are very closely related, and you can actually infer the result of one from the other. But technically, the confidence interval is a range of values, or is two numbers that tell us where we believe the population mean will exist. And the hypothesis test is a statistical procedure for asking a question about the population mean. So for example, question 3 on slide 24, this poses the type of question you might expect to see in a hypothesis testing situation. So this is asking, is there evidence essentially that the average amount of liquid in a 2.4 of beer is equal to 330 milliliters? So is there evidence that mu equals 330? This would be a standard type of single sample hypothesis testing question. All right. To perform a hypothesis test, we start off by checking the same assumptions that we would have checked for a confidence interval. So we need to determine if we collected a simple random sample, and we need to determine if there's evidence of normality. Once we have our assumptions checked off, we then move through the 6 steps, or we can then move through a 6-step process for conducting hypothesis tests. Some professors teach this as a 4-step process or a 5-step process, just depending on what you do with step 2. But in general, this outline includes all of the different components that you need to touch on when you're working through a hypothesis test. So on step 1, we declare the null and alternative hypotheses, of which there are 3 different types, and we'll review these in a bit. Step 2, we decide or we state the significance level of the test. This will almost always be given to you, but in the event that it is not given to you, you can typically assume that it's equal to 0.05. On step 3, we compute the test statistic. Just like with a confidence interval, if we have sigma, then we use a z-score, or we use the standard normal table. If we do not have sigma and we're using the sample standard deviation, then we would use a t-value. On step 4, we would calculate either the critical value or the p-value for the test. You don't have to do both. I will illustrate both so you have examples of it and for refreshment purposes. But they will always agree with each other. So it's actually redundant to calculate both methods or to use both values. On step 5, we would determine whether or not we should reject the test, or reject the null, I should say. And then on step 6, we would interpret the results of the test. So as I mentioned before, there are actually 3 different types of hypothesis tests that we can consider. They are usually referred to as the two-tailed test, the upper-tailed test, or the lower-tailed test. The rationale for their names is based off of the alternative hypothesis symbol. So you will notice that in the case of the two-tailed test, we have the does not equal sign in the alternative. In the case of the upper-tailed test, we have the greater than sign in the alternative. And in the case of the lower-tailed test, we have the less than sign in the alternative. The alternative hypothesis always reflects the question of interest. In fact, when we first teach hypothesis testing, We usually teach the null hypothesis to always represent equality. The reason that we consider the null hypothesis to always represent equality is because students can get confused as to whether or not the null hypothesis or the alternative hypothesis is reflecting what you are interested in testing. So whenever we pose a question about mu, that question should always be reflected in the alternative hypothesis. The null hypothesis is the hypothesis of equality, but strictly speaking, we can write, in the case of an upper tail test, h naught mu less than or equal to mu 0, because if we reject, we're able to reject all of those different cases as well. So both the equality and the less than or equal to, in the case of the upper tail test, are correct, but this is technically a little bit more correct because you're considering all of the different cases that are opposite of what you are asking in the alternative. The upper tail test and the lower tail test are also called one-tailed tests. This has to do with where we look for the critical value and the p-value based off of these types of alternative hypotheses. When we are conducting hypothesis tests, there are two major types of errors that we have to be aware of. The first type of error is what we call type 1 error. This is when we reject a null hypothesis that is actually true. The second type of error is called type 2 error, and this is when we fail to reject a null hypothesis that is actually false. So the type 1 error and the type 2 error are not complements of each other. They are two distinct cases that have different conditions. We can express the probabilities of type 1 and type 2 error using the symbols alpha and beta. So alpha and beta generally mean the probability of committing either one of these errors. And strictly speaking, this is also written as the probability of reject H0 given H0 true. This is the probability do not reject H0 given H0 false. Okay. So you can see from these probability expressions that the condition, so given H naught true versus given H naught false, are not the same. So these conditions being different is why we would say that alpha and beta are not complements of one another. That being said, alpha and beta do have a relationship with each other. And we typically describe the relationship as a seesaw style of relationship. So if you imagine, for example, a teeter-totter like this. Okay. So on one end of the teeter-totter, you have beta, and then on the other end, you have alpha. As alpha goes up, beta goes down. As beta goes up, alpha goes down. The result is that if we have alpha here and we have beta here, their relationship looks something like this. So it's somewhat quadratic, okay? So it is true that as one increases, the other decreases, but it is not a linear or complementary relationship. We typically describe it as kind of a seesaw style relationship. So the more we push one down, the other one has to go up as a consequence. It's also worth pointing out that 1 minus beta is called the power of the test. And the power of the test is the probability of rejecting H0 given H0 false. Okay. So the power is the complement of type 2 error, and this is something we typically want to be as high as possible. So if you think about this problem, what we have established are that the probabilities of committing the two major types of errors are related to one another. Their relationship can be described as sort of an inverse relationship in the sense that as one goes up, the other goes down, but it's not a strictly linear relationship or a complementary relationship. Power, which is the probability of rejecting a false null hypothesis, is something that we would want to maximize. So as we push the power higher and higher, we push the probability of type 2 error lower and lower. However, in doing this, the probability of type 1 error also becomes higher and higher because it does go up as beta goes down. So there's a compensation that has to be made between maximizing power and minimizing both type 1 error and type 2 error. Now, most often when we conduct hypothesis tests, our strategy is to fix the type 1 error. And this is actually done on step 2 when we declare the significance level, because as you can see here, the probability of a type 1 error is equal to alpha, which is the same thing as the significance level. So effectively what we do is we fix the type 1 error to be some acceptable value, usually 0.05. And then we aim to try and maximize the power as much as possible based off of that fixed value of alpha. And most often this is done by trying to increase sample size as much as possible. Okay, on step 5 of the hypothesis testing procedure, we can compute either the critical value or the p-value. Again, you don't have to do both. Most often you'll be given a choice, so you can use either approach. They will always agree with each other, the critical value and p-value approaches, as they are meant to do the exact same thing. The general idea with a critical value is that we are establishing a cutoff between what we would call the rejection region and the non-rejection region. Now, from a general point of view, I guess you could say, the idea here is that on step 3 of the hypothesis test, you have computed a test statistic. The larger that test statistic is in magnitude, the more likely it is that you should reject the null hypothesis. So what I mean is, if you have a test statistic of, say, that has a value of, say, 10, if you have a test statistic whose absolute value is 5 or 10 or 20 or 30, these would be considered very large values, and most likely you are going to reject. Whereas if you had a test statistic whose absolute value is, say, 0.5 or 1 or 2, it's not as clear whether this would be considered large enough for rejection to occur. Now, the idea of a value being small or large is somewhat arbitrary, so we have to establish a cutoff point. That is what the critical value is. The critical value tells us whether we would consider the test statistic to be big enough to warrant rejecting the null hypothesis. And the critical value is determined simply by the significance level of the test, and in the case of the student t distribution, the degrees of freedom as well. The other approach to determining if we have evidence against the null, determining if there's evidence for or against the null, is the p-value approach. And the rationale behind the p-value approach is the same as the rationale behind the critical value approach. Now, the p-value, by definition, is a probability. The formal definition of the p-value is the probability of observing a test statistic more extreme than the one observed under the assumption that the null is true. In the context of hypothesis testing, we use the p-value as a measure of strength for, measures the strength of the evidence against the null. Okay, another way to think about this, we use the p-value as a probability to determine if we should or should not reject the null hypothesis. And more strictly, we think of the p-value as a probability of whether or not there is evidence that the null hypothesis is true. So the idea is, since the p-value is a probability, it exists between 0 and 1. If the p-value is close to 0, this would indicate a lack of strength in the null hypothesis, or it would indicate a lack of evidence that the null hypothesis might actually be true. So a p-value very close to 0 indicates that the null hypothesis is unlikely. A p-value very close to 1 would indicate that the null hypothesis is likely to be the true case. So p-values close to 0 indicate lack of certainty in the null. P-values closer to 1 indicate certainty in the null. Now, if we want to use the p-value for rejection, what we have to determine is how small is small enough for the null hypothesis to be rejected. So for example, you could argue that if the p-value is 20%, I mean, that's a fairly small percentage. That's about 1/5 of the time this event is going to occur. Is that small enough to warrant rejection of the null? It's arbitrary, I guess. Or let's say the p-value is 10%. This is saying effectively 1 in 10 times this event is going to occur. Is that small enough to say that it's rare? In order to determine if the p-value is small enough to reject the null, we establish a cutoff point. That cutoff point is the significance level. So the significance level, again, acts as essentially a boundary between what we would consider to be a rare event and what we would consider to be a non-rare event. So in general, our strategy is to say, if the p-value is smaller than or equal to the significance level, we will consider the null hypothesis a rare event, and we will reject the null. Whereas if the p-value is larger than alpha, we would consider the null hypothesis to not be a rare event, and we would not reject it. So that explanation is actually what you would want to consider when you're trying to answer question 4 on assignment 1. I have been asked a couple of times about this question. We hadn't actually reviewed it in any detail until now, but that is the rationale for why we establish a cutoff. Because basically, without a cutoff being established, so without declaring a significance level, what it means to be small enough in terms of a probability and what it means to be large enough in terms of probability doesn't have any meaning, because you could argue anywhere on that scale as being a point for it being small, too small, or too large. Does anyone have any questions about that idea? All right, so let's look at an example of how we would work through a hypothesis test. So we have here, a researcher collects a simple random sample of 16 pieces of tuna and finds that the average mercury content of the sample is 0.74 parts per million. Given that the mercury content of tuna is known to be normally distributed with a standard deviation of 0.08 parts per million, is there evidence that the true mean mercury content is greater than 0.4 parts per million at alpha equals 0.05? Okay, so there's quite a bit of stuff to unpack here. So let's just start down by writing out what we know. So first off, our sample size is 16. The mean of the sample is 0.74. The population standard deviation is 0.08, and mu is declared to be 0.4. We want to conduct a hypothesis test to determine if there is evidence that the true mean content exceeds or is greater than 0.4. So the assumptions of our test are 1, that we collected an SRS, and 2, normality. So this would be normality of the population of interest, or normality of X bar. Now in the question, we are told that we have an SRS. That's one of the first points that is made. And then we are also told that mercury content of tuna is normally distributed. So that would be our second assumption. So now what we can do is begin to work through the steps of the test. All right, so on step 1, we're going to have the following: h naught mu less than or equal to 0.40 versus ha mu greater than 0.40. All right, so let's think about this for a second. I have the greater than sign in the alternative hypothesis. The question that we are being asked is there evidence that the true mean mercury content is greater than 0.4? So my alternative hypothesis is reflecting the question of interest. Okay. So what the question that I am asking about the mean content of the tuna is being reflected through the alternative hypothesis. All right. On step 2, we declare the significance level, which is alpha equals 0.05. On step 3, we compute our test statistic. So on step 3, we have Z equals X bar minus mu over sigma divided by the square root of n. So notice that I'm using a Z score on step 3 because I have sigma, which is the population standard deviation. So now I plug in. And this gives me a Z score of 17. Okay. On step 4, I can take either the critical value approach or I can take the p-value approach. So if I take the critical value approach, I start by sketching the standard normal curve. So here's my standard normal distribution. We're centered at 0. My critical value is going to be a Z score that puts 0.05 of the area into the upper tail of the curve because we are conducting an upper tail test. So the fact that we have the greater than sign in the alternative indicates that the rejection region has to be on the right side of the curve. Okay, so here I have Z. This is going to be subscript 0.05. And then that means that this red shaded part here, this is a size of 0.05. Okay. So again, the alternative hypothesis tells us where the critical or the rejection region is located. So because we have a greater than sign in the alternative hypothesis, that means that the rejection region is in the upper tail of the curve. As such, the critical value must also mark the upper tail of the curve. So we have a critical value that puts 0.05 of the area under the curve into the upper tail, and the remaining 0.95% of the area must be to the left of that critical value. So if we go to our standard normal table, what we are looking for here is the, actually, let's do it the easier way. So we have a Z subscript 0.05. So if we go to the T table then, and we go to page 2 of the T table, and we scroll down to the very bottom, what we are looking for here is the Z score with 0.05 in the upper tail, so Z subscript 0.05, and that gives us 1.645 as the critical value. So our critical value here is Z equals 1.645. And then what we would do is we would place on the axes where the test statistic falls. So if 0 is in the middle, 1.645 marks the boundary between 0 and the rejection, or between the rejection region and the non-rejection region. Our test statistic is going to be way over here somewhere. So that'll be Z equals 17. So the test statistic is very far into the tail of the distribution, and that would be an indication that we should reject the null hypothesis. Any questions? Right. So in general, for the assignments and the tests and whatnot, if the assumptions aren't given, then, and you can't verify them, then work through the steps of the test. And then in the concluding statement, give the condition that this assumption has to be verified. And then you can write out the standard conclusion for the procedure. But it's worth saying that on most practical problems, so the problems that you see in the lab, for example, you'll always be able to check the assumptions because you'll be able to build QQ plots, for example, to verify normality. Does that help? All right. Okay, so the p-value is found in a similar way to how the critical value is found. So first off, with the p-value, we start by marking down where the test statistic is located. So our test statistic is equal to 17. So that's going to be really far into the upper tail of the curve. So we'll have Z is equal to 17, kind of like up in this area here. And then we have this green shaded part here. This green shaded part here represents the p-value. Right. So what we can determine from looking at this illustration is that the p-value is the probability that Z exceeds 17. So the p-value itself is actually just a probability underneath the Z curve, or the standard normal curve. So it's just the area underneath the curve that is greater than 17. So in order to work out this problem, we actually will require the standard normal table here. So we're looking for, what we're going to do in this case is look up Z equals 17 on the axes of the table. Now you'll notice that the maximum value in the table for Z equals 17, or the maximum value in the standard normal table is 3.9. This note at the bottom says for Z greater than or equal to 3.9, the areas are 1.000 to 4 decimal places. So this note is telling us that the area below any value greater than or equal to 3.9 is effectively equal to 1. So in our illustration, what we have determined is this area here is approximately 1. So the area to the left of our test statistic is approximately equal to 1. The p-value, let me just write this on the next slide. So since the probability that z is less than or equal to 17 is approximately equal to 1, the p-value, which is the probability z exceeds 17, which is equal to 1 minus the probability that z is less than or equal to 17, is approximately equal to 1 minus 1, which is approximately 0. So the p-value for this particular test is approximately equal to 0. So therefore, on step 5, we would say reject H0 since test statistic is in rejection region. Okay. And then this, this statement here is the same thing as saying reject H0 since Z is greater than Z 0.05. Or we can write reject H0 since the p-value is less than alpha. And you can see here that this is one of the reasons why the p-value ends up being used so often, because no matter what type of test you're working on, the rule for using the p-value is always the same. So you can always just compare the p-value to the significance level directly, and if it's smaller, you would reject the null. Whereas with the test statistic, or with the critical value approach, the statement that we would use for rejecting versus not rejecting depends on where the rejection region is located. All right, step 6. So in step 6, we're just going to conclude our test. So the standard conclusion for a hypothesis test reads something like this. At the 5% significance level, the data do not provide sufficient evidence to suggest that the data do provide sufficient evidence, just that the population mean mercury content of tuna exceeds 0.40 parts per million. Okay, so that's a hypothesis test using the standard normal curve. In this case, it's an upper tail test. Does anyone have any questions? Okay. All right. Okay, so another example, the National Funeral Directors Association reported that the average cost of a full service funeral in 2005 was $6,500. A simple random sample of 36 funeral homes gave X bar equals $6,819. If sigma is 1,265, test the claim that the true mean is not equal to 6,500 when alpha equals 0.05. Okay, so we have n is equal to 36. We have x bar is equal to 6,819. We have sigma is equal to 1,256. And we have mu is equal to 6,500. All right. For the assumptions, for the first assumption, we're fine because we're told in the question that we have an SRS. For the second assumption, which is normality, we are also fine. Why are we okay here? Well, n equals 36. This is greater than 30. So CLT applies. Okay. So for the normality assumption, we can use the central limit theorem to state that x bar is approximately normal because our sample size is larger than 30. All right. So on step 1, we are going to test whether or not there is evidence that the true mean cost of full service funerals is not equal to 6,500. So our null hypothesis will be the hypothesis of equality, and our alternative hypothesis will be the hypothesis of inequality. On step 2, we will state our significance level. And then on step 3, we will give the test statistic, which is x bar minus mu divided by sigma over the square root of n. So this is 6,819 minus 6,500 divided by 1,265 over the square root of 36. And this is 1.513. Oops. All right, so if we take the critical value approach, with the critical value approach, we have to mark down where the rejection regions are located for this particular problem. This is in the alternative hypothesis, we have the does not equal sign. So this is what we would call a two-tailed test. So we call this a two-tailed test because we're going to have a rejection region on each side of 0. And this is a result of the does not equal sign in the alternative hypothesis. So we're going to have Z subscript alpha over 2 in the upper tail, and then we'll have Z subscript alpha over 2 in the lower tail. So notice that when we have the two-tail test, we are splitting the significance level into each of the tails. So this is going to be Z alpha over 2, which is 0.05 over 2, 0.025. And then in the upper tail, we'll have Z subscript 0.025 as well. Okay, so this red shaded part here and this red shaded part here, this is size 0.025, and this is size 0.025. Okay, so in the upper tail, we have the Z score on 0.025, and then sorry, in the lower tail, we'll have the negative, I apologize, of that same Z score because the curve is symmetric, okay? So in the lower tail, we have negative subscript 0.025. Okay, so if we go back to the t table here and we just go to the end of our t table, we're just looking for z subscript 0.025, which is this value right here. So the z score for, or the critical value for this hypothesis test will be 1.96 in this case. Okay, so in the lower tail, we'll have negative 1.96, and in the upper tail, we'll have positive 1.96. The test statistic was 1.513. So if we mark down the test statistic, we can see that that's located right about here. Okay. So based off of the illustration of the critical value, we can see the test statistic is not inside the lower or upper rejection regions. So this will be a situation where we do not reject H naught. If we take the p-value approach, we're going to mark down our test statistic in the upper tail, and we're going to mark down the negative of that value in the lower tail. Okay, so those areas are going to be about the same size, or they are exactly the same size. So the p-value is equal to the probability that z is less than negative 1.53 plus the probability z is greater than 1.513. Okay, now this, because these areas are the same size, this can be written as 2 times the probability that z is less than, and this is also equivalent to 2 times the probability z is greater than. Okay, so these are all the exact same expression. So what we will do now is we will go to the standard normal table. The standard normal table is a cumulative table, so it gives us the area to the left of the z score. So if we look up negative 1.51, which is this value right here, we get 0.0655. So this is going to be the size of the area in the lower tail. Okay, so this here is a size 0.0655, which means that this is also a size 0.0655. So the p-value is 2 times 0.0655, which is 0.1310. So now we can see that based off of either the critical value approach or the p-value approach, we're going to reject H naught. So on step 5, we have reject H0. Okay. So we can reject H0 since Z, in this case, we would have to write, well, let's just say since test statistic not in rejection region. Now, if you wanted to write this in a symbolistic way, you can say since absolute Z so it would have to be, since absolute Z does not exceed Z alpha over 2. That would be one way of expressing it. Okay. Or we can reject H naught since the p-value is less than or is greater than alpha. Sorry, it should be greater than. Yeah, for the p-value, right? Yeah, greater than. Thank you. Okay, and then I'll just finish this up here. So now we can just say at the 5% significance level, the data do not provide sufficient evidence to suggest that the average cost of full service funerals is different from $6,500. Sorry, so that says at the 5% significance level, the data do not provide sufficient evidence to suggest that the average cost of full service funerals is different from $6,500. Right, so that's our second illustration of a hypothesis test using the standard normal distribution. Does anyone have any questions?
Brian?
Yes.
Are we rejecting or not rejecting the null hypotheses?
Thank you.
Perfect. Thank you.
Thanks, sorry.
It's okay.
Any other questions or clarifications? So if there's no questions, I'll stop there for today. On Monday, I'll go over finding probabilities using the student t table, and then we will look at 2 examples of hypothesis tests using the student t distribution. And then following that, we'll start lecture set 3, where we will discuss 2 sample hypothesis tests. And as a reminder, so the first assignment is due tonight. If you just got enrolled today, please send me an email and just let me know. The lab assignment 1 will be due next week on Friday, and then assignment 2 is due 2 weeks from today, and I'll post that but before the end of the day. So have a good weekend. If you have any questions, let me know, and I'll talk to you guys on Monday.